Last time on 3.2, we talked about a first derivative test, which is the tool that we use to find the relative extrema, and we also talked about the absolute extrema, okay? And make sure you pay like close attention to them. And then one of the tools that we use to find like all those extremas was by the table of signs, okay? So make sure you know what the table of signs mean and how to do it, okay? So today, let's take it to the next level and talk about a second derivative test, which will relate to the concavity, like the U shape, and you will see why in a second, okay? So before we get into the content of 3.3, let's review some old concept. We have the first bullet in here is that we already know that locating the intervals over which a function f is increasing or decreasing is helpful in determining its graph, right? Like, so like on last section or like 3.1 and 3.2, I don't remember, but either of them we talk about increasing and decreasing interval, right? And it will help a lot in terms of, you know, like graphing, okay? And in this section, we'll see that locating the intervals on which f prime increases or decreases can also determine the graph of f is curving upward or curving downward, okay? So curving upward or curving downward in here, we referred to the term concavity, okay? So what does it mean by concavity? It means like concaving upward or concaving downward, okay? For concaving upward, you're gonna have like a U shape in here. So this one, if you extend it, it's gonna look like a U shape, right? Like, which is, you know, like a regular U shape. And concurving downward, if you extend this thing, it's gonna look like an upside down U. So concurving downward is gonna look like this, okay? So upward, it means that your f prime is increasing or f prime is like positive. Downward, it means that your f prime is decreases or f prime is negative, okay? So just a little bit of, you know, like notation or like more details on each of the picture in here. For the first picture of concaving like upward, a curve lies above its tangent line, okay? So as you can see, okay, first of all, let me like draw the tangent line in pink in here. So say if we're looking at this point in here, then the tangent line is like right here, right? And as you can see, the red curve in here is like on top of the pink line, right? And say if you want to consider another point here where we have this tangent line right here, same deal, we're gonna have the red curve lies on top of the pink line, okay? And another example is that if you look at the line, the point here, the tangent line is like right here, right? And same thing as before, the red curve is on top of the pink line, okay? Whereas for the second picture, if you can consider like a point here, then the tangent line for it will be like this. And as you can see, the pink line is lying on top of the red curve now, right? Because we talk about concaving downward, okay? And same thing happens for like this point where this is like the tangent point, or this point here where this is the tangent line, okay? So what does it mean for concavity, right? Let f be a differentiable. Let f be differentiable on an open interval I. The graph of f is concaving upward if f is increasing on the interval, okay? And then it's concaving downward if f prime is decreasing on that interval, okay? So my bad, there's supposed to be like a prime in here. That's why I'm gonna fix it really quick. Let me put it in, I'm gonna like green to catch your attention. So this one we're talking about f prime, and the other one is also about f prime, okay? And if you need like some reference in here, you can look back at like the previous notation or like the previous pictures in here, okay? So f prime increasing is for the first picture, and then f prime decreasing is for the second picture, okay? All right, so next up we have concavity, points of inflection, right? So for the first derivative, if we set it equal to 0 or we set it equal to, you know, like undefined, we're gonna get the critical numbers, right? If we do the same thing but for the second derivative, we're not gonna have like critical numbers anymore, but we're gonna get inflection points, okay? So test for concavity in here, let f be a function whose second derivative exists on an open interval I. If the second derivative of f is greater than 0, meaning it's positive, meaning that f in here is like increasing, f prime is increasing, or we have like a U shape, f in here would be open like upward. So in here to link it, greater than 0 or being positive for concaving upward, less than 0 or being negative is for concaving downward, okay? And we're talking about the second derivative in here, okay? And this is like f, not f prime, okay? So concavity is about the relationship between f, the original function, versus the second derivative, okay? So the second derivative in here could be less than 0 or like greater than 0. It means that the original function, it will look like a U shape or an upside down U, okay? If the tangent line to the graph exists at the point at which the concavity changes, say you're gonna get something like, okay, you're gonna see it in a second when we talk about like the two pictures right below it, okay? Then the point in here, we call it the point of inflection, okay? If the graph of a continuous function has a tangent line at a point where its concavity changes from upward to downward, so notice that in here we're talking about upward to downward, right? So then that is like point of inflection. And then for another scenario, if you have it change from downward to upward, it's also called a point of inflection or the inflection point, okay? If a point C, f of C, is a point of inflection, so now we know that it's a point of inflection, okay? Then either like two things can happen, right? Like the first derivative of it equal to 0, or it equals to like undefined, okay? And I feel like this should be the second derivative, not the first derivative, because this is like the definition for the critical numbers. So let me change it really quick, and I'm so sorry for this. I'm gonna like upload, I'm gonna fix the note, okay? So this one, it should be like double prime in here, and this one, it should also be double prime, okay? All right, so what does all that means, right? So it means that, let me put it back in red in here. Say for this branch in here is concaving, like if you were to extend it, it's gonna look like a U shape like this, right? So this part in here is, it looks like this, while the other part, it looks like a U shape, right? So we having like from like a downward to changes to an upward U. So this one is like downward. I'm just gonna put like down, and this one is like upward. Let me put it in pink. And the point where that change happens in here is like this point here. Let me put in green, like this one in here. So we're gonna call this one the point of inflection, or IP for inflection point. Okay. And then if you want, you can label it as, you know, like 0, 0 in here, because it's like right at the origin. And the reason why is that if you take the second derivative of this function, you're gonna, and set it equal to 0, you're gonna get x equal to 0. So let me do it really quick. So the first derivative of this function in here, I hope everyone is like cool with it by now. It is 3x squared, and then the second derivative, it should be 6x. Okay, and if I set it equal to 0, like here, okay, let me change it into another color for like different procedure. So the green in here is just for like finding the derivative, right? And then the blue in here for like finding the inflection points, okay? So now that we have this relationship in here, we're gonna divide both sides by 6, and we're gonna end up having x equal to 0. And now that we have the x value already, we're gonna plug it back into the original function to get the y value. So y in here equals to 0 to the third power, which is also 0. So then if we put the x and y together, we're gonna get the point 0, 0 in here, and it's our point of inflection. Okay, and then similar things happen for the second picture in here. We have like two branches. This one is like an upward U, and then the other one, fortunately, is also like an upward U, right? Like if you connect them all together and use like one color for it, that works too. That works too. But I'm just trying to say that like this breaking point here, it doesn't mean anything because we don't have any changing, right? Like it doesn't change from up to down, or like from down to upward. So this in here is not the inflection point, okay? Like it's not the inflection point because there's no like changing in the shape of the U in here, okay? And because it's not the inflection point, we don't have to go through the process of finding the second derivative and setting it equal to 0, because we don't even have an inflection point, so then we don't have to find, okay? Now let's talk about the example that goes with that objective. Okay, so discuss the concavity of the graph of f and finds its points of inflection. Okay, so two things we have to do, right? We have to find the concavity in here, meaning we have to find the interval where f concaves upward and where f concaves downward. And we also have to find the point of inflection, right? So how can we do that? Well, first thing first, we're gonna look for the domain in here. just to get rid of all the discontinuities. So the domain of f in here, it equals to what, like we have to set the bottom equal to 0 in here. And if you do it, you're gonna get x equal to plus minus 1, right? Why is that so? Because if you were to plug in 1 or negative 1 onto this function right here, it's gonna give you 0 on the bottom, and we all know that we cannot divide anything by 0, right? Like that's undefined, right? So the domain in here, it equals to like r for all real numbers except for plus minus 1, okay? So plus and minus 1 in here is like a big no-no for this function, because it doesn't make sense if we plug in plus 1 or like minus 1 into the function of f, okay? And because we're talking about a concavity in here, the keyword for it, so then we have to find a second derivative, right? And then to find the points of inflection, we have to set the second derivative equal to 0. So let's get to that, right? So the first derivative, f prime of x in here, it equals to what? I'm gonna apply like the quotient rule in here really quick, okay? And if you like need more help or like more explanation on how to carry on the quotient rule in here, let me know, okay? But for the sake of time in the video, I'm not gonna like do it like, you know, like I'm not gonna do it like as detailed as it could be, okay? But again, please ask me questions if you like not sure what I'm talking about. So in here is quotient rule, so we're gonna have like f equals to x in here, and then g equals to x squared minus 1, and then f prime equals to 1, and then g prime equals to 2x, and this should be like a 2 in here. Okay, so what we're gonna do is that for quotient rule, we're gonna do f prime g, which is x squared minus 1, and then minus the outer cross, which is f g prime, and that is 2x squared in here. And then we're gonna do g squared on the bottom, which is x squared minus 1 squared. And I'm gonna go ahead and erase this one first so that I have space in here to combine the like terms on the top part. And if I haven't told you guys this one already, like don't ever touch on the bottom, okay? Like regardless of what bottom you have in there, just keep it as what it is. Don't ever touch on the bottom. Like don't expand the bottom, like don't simplify the bottom or anything. Like keep it as what it is, okay? So then the top part in here, if I go ahead and combine the like terms, I'm gonna get negative x squared minus 1 in here, okay? And that is my first derivative, right? So now carry on, I'm gonna find a second derivative, f second prime, or like f double prime of x. So same deal in here, I'm gonna do the f and g thingy again. So my f in here is negative x squared minus 1, and then my g in here is x squared. Okay, that's like ugly writing. You know what, let me just do it in here. Okay, so my f in here is negative x squared minus 1, g is x squared minus 1 squared, and then f prime in here is negative 2x, g prime is, what is it? I'm going to apply the chain rule in here together with the power rule. So again, I'm like fast forward because like I assume that we all get used to the process of finding the derivative, but if that's not the case, let me know, okay? So then the chain rule in here is 2x, and we have a 2 from the power rule, so that is like 4x. And then times x squared minus 1. Okay? Okay, so now we're going to apply the quotient rule in here. It means that we're going to multiply these two together, so that gives me what, a negative 2x, and then the group of x squared minus 1 squared, and then minus the other 1. So what does it look like? It's gonna look like, okay, first of all, I'm gonna pull out a negative in here, okay? So it's gonna look like a negative, and then x squared plus 1. Okay, so to multiply this by this, okay, if you want, you can like multiply it out by FOIL, and then, you know, multiply every terms by negative 4x at the end. But I have like a little trick to myself. I know that there's a formula that says that a minus b times a plus b equals to a squared minus b squared, okay? So, I mean minus, not plus. So I'm gonna go ahead and apply this formula in here, and I'm gonna treat, wait, minus, okay, there we go. And I'm gonna treat this one like a and this one like b in here, okay? So if I multiply like these two together, I'm gonna get a negative 4x outside, because I haven't like touched them yet. The negative in here is for this negative, 4x in here is just for this 4x, right? And if I multiply like the inside, I'm gonna get x to the 4th power minus 1. And if I were to FOIL them, I'm gonna get negative 4 x to the 5th power and then plus 4x. Okay, and because I have like a negative from like, you know, a part proportion rule, I'm gonna apply it to this negative in here and also this positive in here to make it a negative. Okay, so technically I'm gonna get a plus in here and then 4x to the 5th power minus 4x. Okay. Alright, so how do we do this? Well, I have to FOIL this one out, like this group out. So let me erase all the work in here and let me FOIL that one out first, just so I can like put it back in the same place in there. So x squared minus, okay, x squared minus 1 squared in here. It means that we're gonna have to draw like 2 group of it, right? And then we're gonna have to FOIL them in, right? And then let me take away the square in here. Okay, if I were to do that, I'm gonna get something like x to the 4th, and then just assume that I'm gonna like fast forward and combine the like terms, okay? I'm gonna get like negative 2 in here, and then x squared, and then plus 1, okay? And before that, I have like a negative 2x in here, so let me just put it back before like the things that I just got after I FOIL them. And I'm gonna distribute the negative 2x inside, so I'm gonna get negative 2x 5th, and then plus 4x cubed, and then minus 2x. Okay, so now for the sake of like the space in here, let me go ahead and copy this down here for like adding them. So I have like plus 4x to the 5th power and then minus 4x. Okay, some of you guys may ask me like why I leave the space in here. Well, I'm trying to arrange them like column wise to combine the lie terms. But if you don't want to do that, that's fine. You don't have to do that, okay? So if I were to combine these two groups together, what do I get? I'm gonna get 2x to the 5th power plus 4x cubed, because it's like empty in here, so I'm just gonna directly like bring it down. And then lastly, I get negative 6x. Okay. I'm thinking, do I need to do this one? Because at the end of the day, like later on, we know for the fact that we have to set it equal to 0, right? So that might be a little bit tricky for us to do it that way. So instead of doing that, you know what? Let me show you guys another like way to do this one. Okay, so the first group, keep it as what it is. You don't have to like FOIL it in to save the time. For the second group, in fact, let's write everything down. So in here, if I'm not wrong, for the second group, we're gonna get what, like a 4 in here, a minus 4 to be more like correct, and then minus, well, negative 4x in here, and then minus 4x to the 4th power, and then what else, plus 1 in here. And for the inside, it should be something like negative 4x and then x squared minus 1 and then x squared plus 1, right? Like this is what we have from the previous step, right? Like without doing a lot of like things, right? And this should be a positive actually. Okay, so let me get rid of this first. Okay, and again, if you have no idea where we got this one, it's from like the second group of multiplying the f with g prime, like just from the setup, okay? But this time I'm not gonna distribute it in, and you guys will see why in a second. Okay, so let me just put it back in here as 4x, and then the group of x squared minus 1, and then x squared plus 1. Okay, and then I'm gonna keep the bottom as what it is, but then I square it up, so it's gonna be like to the 4th power in here. Okay, and now I'm gonna factor out the common things, right? So let me highlight the common things in here in blue. So I have like this group in here in common, and I have like the x in common, and then the 2 and the 4, I'm gonna get like a 2 in common, and I'm gonna also pull out a negative. Okay, so in short, it's gonna look like negative 2x, and then one group of x squared minus 1. Open the big parentheses in here to stuff in whatever's left over for the first group and the second group. For the first group, I end up having just like one group of x squared minus 1. For the second group, I end up having like a negative 2 from the 4. And I also have the group of x squared plus 1. Okay? And if I want, I can simplify this one, right? So this in here. Okay, first of all, let me get rid of this. So that in there, it looks like x squared minus 1 and then 2, negative 2x squared minus 2, right? If I were to combine the like terms, I'm going to get negative x squared minus 3. Okay? So let me erase all of this and then just stuff like negative x squared minus 3 into the brackets. Okay? So that's there. And then that's what I have inside the bracket, and I'm missing a parenthesis in here. Okay, and then this is like all over what, x squared minus 1 to the 4th power, right? And to make it look like nicer, notice that in here we can also factor out like a negative, right? So that negative together with the negative in front, we'll lose the negative in front of the 2, right? And that will change this, like the size in front of the x squared and the 3 into like positive. Okay, and what's next? Well, we're gonna apply the table of side that we had from before. So we're gonna set each of the top and bottom equal to 0. So what happens if the top equal to 0, and what happens if the bottom equal to 0, right? The bottom is easier to deal with. For the bottom equal to 0, I'm gonna get x equal to plus minus 1. For the top equal to 0, I'm gonna get x equal to 0, just for like this part in here. X equal to plus minus 1 for that part in the second circle. And lastly, for this group in here, it can never be equal to 0, right? Because just imagine if you have like an x squared plus 3 equal to 0, you're gonna get like x squared equals to negative 3, and then you're gonna take the square root of both sides. But then there's a problem, we cannot take the square root of a negative number, right? So this one in here, you can just ignore it, okay? Because it's always like positive. Okay, and if you want to think about, like, if you like square a number, no matter what value of that number is, you square it up, you're gonna get a positive number, right? And then you add 3 to it, which makes it more even positive. So you can disregard this term in here. Okay. So let me get rid of this side work in here, and then let me put back like the table of side. Let me put it in green in here. Okay, so what do? Well, how many values do we have in here, right? We're gonna have like 2 values in here, and 0 plus minus 1, right? And if you notice, well, actually, how comes the plus minus 1 appears like 2 places for the top and bottom, right? It means that we actually can cancel like some of them out, right? So let me go back a little bit in here, and actually I can cancel one group in here together with one group in here to replace like the power 3 in here. So in fact, to set the top part equal to 0, I'm only gonna get x equal to 0. Okay? And for the bottom part, it doesn't change anything. You're still gonna have like 3 groups of x squared minus 1. So to set it equal to 0, it means that the inside equal to 0, and that also means that x equal to plus minus 1. Okay? So now back to the table of sign here. So then the first line here is for the x value, and then the second one in here would be for the top part, which is just 2x, because I told you guys you can throw away this one. That's for the top part. So let me put like t for top. And then the bottom part, it is x squared minus 1 cubed. Bottom part. And lastly, we're gonna get what? We're gonna have to find like the psi of the second derivative. So this is the second derivative, which is like the whole function in here. Okay? Which is like, okay, let me make like a note in here. Let me rewrite this one in here. It's gonna look like 2x and then x squared plus 3 over x squared minus 1 cubed. And this is the second derivative that we're talking about. Okay? And then lastly, you have to plug it back to the original function, this one in here, to find the y values. So you can call this one like f of x or just y value that you want to, okay? Alright, so this one is the original function. This one is a second derivative, just to make sure we're on the same page, okay? So for the value of x, we know that it always goes from negative infinity all the way to positive infinity. And in between, we have like 3 values, right? We have like x equal to 0, and we also have x equal to plus minus 1, right? So let me change the color for this one to, I don't know, like brown here. Okay, so we're going to arrange them from least to greatest. So it's going to look like negative 1, 0, and 1, okay? So underneath of the top part, we're going to get x equal to 0 at, you know, like 0. So that's a 0 right here. And then for the bottom part, we're gonna get a 0 underneath of the plus and minus one. So that's right here and here. And for the rest of them, I'm just gonna put like numbers in here, okay? Because it could be like a number, but we're just like too lazy to calculate it out, okay? When it comes to the second derivative, we're talking about this one right here, right? So if the top equal to 0, then like if you divide, you're gonna get a 0. But if the bottom equal to 0, it means that you're not gonna get like a good number, or you can just say undefined or doesn't exist. Okay. And then for the original function, we know that by the domain, we cannot take plus minus 1, right? So underneath of the plus minus 1, we're gonna put like 0 and 0 in here. For 0, you're gonna have to find it by plugging it back into the original function in here. So that it means that we're gonna get like 0 divided by 0 squared minus 1. If you put all that into the calculator, you're gonna get 0, and this 0 in here is for the 0 in here. And actually, let me change the color for this one because I think it's like the whole like new procedure, I guess. So let me put in purple. This 0 in purple is this 0 in purple for what we get after we plug the x into the original function. Okay. Now let's talk about the table of sides in here. So let me put it in, I don't know, orange. Can you see this? Okay, that's a good color. Okay, so between okay, so we need to look for something that less than -1, right? I'm gonna go for -2 in here, and in between I'm gonna do, I don't know, like -0.5. But like I said from the previous like section, if you don't like -0.5, you can go with -0.1 or -0.9. Doesn't really matter, okay? And for the next spot, I'm gonna do 0.5, and then for the last spot, I'm gonna do 2, okay? So if you go ahead and plug all of that into the calculator, you're gonna get the size at below. So this is like negative, and then negative, and then plus in here, and then plus in here. And then for the bottom, we got plus, minus, minus, plus. And lastly, if you divide everything, minus divided by plus is a minus, this is a plus, this is a minus, and this is also a plus. Okay? The last round here, you don't have to find a size anymore because like you don't have to. Okay, so what do we do here? Well, we have to find a concavity, right? So this line here will tell you where, like which interval, on which interval f concaves upward or downward, right? So let me put it in, I don't know, like red in here. So it means that from -infinity to -1, f in here will concaving down because of that negative in there. And for this positive, I'm gonna have like f concaving up, and then negative for concaving down, and then this one is for concaving up. Okay? So from what value, like on what value it changes the sign, right? So this one, it changes from here to here, it changes from here to here, and also it changes from here to here, right? But unfortunately, like -1 and 1 are not in the domain, so the only answer we got in here is 0. So 0 is the only inflection point that we got. And if we want to put it back as a point, we have to use the x and y coordinate, right? So the answer for this one in here is that the IP, the inflection point, it is 0, 0. Okay, and this is it. And for your part, you have to do the other problem, so let me put it in green. Okay, recap, what do we do? First up, find the domain. Let me put it in, what color do you guys, okay, this color, I don't even know what it is. I like yellow brown, yellow orange, whatever. This is first step in here, you have to find the domain. Second step, you have to find the first derivative. Third step, find the second derivative. And then after that, you have to set it equal to 0 for the fourth step in here. And once you get it equal to 0 in here, you have to solve for the x's for both the top and the bottom. That would be the fifth step. And after that, oh, by the way, during like on the third step in here, make sure you simplify to all, like to the most that you can. Okay, like just like my example in here, make sure you always simplify it. Okay. And then we'll talk about fifth step in here while we're getting like all the critical numbers, or in this case, like all the points in the table of psi. And then sixth step in here, we have to make it like as like a table of size in here. And then make sure you figure out like which one changes for the psi of the f double prime to figure out the shape of the original function. And seventh step, last step in here, conclusion. Okay. So now what do we get for second objective? We're going to talk about a second derivative test. Okay, so what does it tell us? It tells us that let f prime, a number, equal to 0, which means that the c in here is a critical number, right? And let f exist on an open interval containing c. If f double prime of c is greater than 0, it means we're going to have a minimum. And if double prime is less than 0, then it's going to be a relative maximum. Okay, how do you remember this one? It's actually really makes like good sense by the picture. So at double prime greater than 0, it means that you're going to have like an upward u, right? And in the upward u in here, the lowest, we're going to have like a lowest point, right? And that's why it's a minimum, okay? For f double prime to be less than 0 in here, we're talking about this shape of an upside down u. And in here, we're going to have a maximum because we have like, you know, the highest point. That's why it's a relative maximum. Okay, what happens if the second prime in here equals 0, right? Well, it could be like an inflection point like what we had in the previous example, or it could be like a point that doesn't even like make the function define, just like how we had in the last example, right? So if it were the case to have the second derivative equal to 0, then the test fail. Like you cannot apply the second derivative test for this case anymore. In that case, you have to go back to the first derivative to determine whether f of c is the relative minimum or maximum, or neither, okay? Alright, so how can we apply that? Well, for my example, we have to find the relative extrema, right? So from before, how we find the relative extrema is that we're gonna go by the table of sign, right? Like we're gonna do it. We're gonna have to find the first derivative, find the critical numbers, getting the table of size, plugging on the numbers into the calculator to get the size, and then going for the conclusion, right? But now that we have the second derivative test, we don't have to do as much of the work anymore. Well, first of all, we're gonna find the first derivative, right? So f prime of x in here, I'm gonna do like it really quick in here. It equals to negative 2x in here for the chain rule, and then for the bottom I'm gonna get like 2 and then square root of 5 minus x squared. Okay, and I learned my lesson this time. I'm gonna like cancel. I'm gonna simplify the expression before I move on. So I go ahead and cancel the 2's, and I have negative x divided by square root of 5 minus x squared. Okay, so now what do I do, right? I'm gonna set it equal to 0. Why is that so? Because it's a part of, you know, like the second derivative test, right? And if I go ahead and set it equal to 0 in here, it gives me x equal to 0, right? So notice that this method is different from the first derivative in the sense that for the first derivative, let me put it in pink, we have to set each, the top and the bottom, equal to 0, and this is like the first derivative test. While for the second derivative test, we only need to set the whole fraction equal to 0, meaning we have to set the top, only the top, equal to 0, and that's all. We don't do anything to the bottom. Like for the second derivative test, we ignore the bottom. Like we don't set it equal to 0. We don't do anything to that. Okay? So that's the difference between the two tests in there. And let me move forward with this example in here. But before that, let me take out all the like side work in here. Okay, so what do we do next? Now we got a c value, right? So now we're gonna have to find a second derivative of this. And the second derivative, fast forward, I'm gonna like do the quotient rule in here, and that gives me negative square root of 5 minus x squared, and then plus 2x squared divided by 2 square root of 5 minus x squared. And I'm gonna go ahead and cancel these first, and then I'm gonna get the like terms in here. But before that, let me put back like the bottom in here. So the bottom is like square root of 5 minus x squared, right? And then the square will cancel that with a square, so you know, like we don't have to worry about the squares on the bottom anymore. In terms of like the top part, just imagine you're gonna get like an over 1 in here, so then the common denominator would be square root of 5 minus x squared, right? And if I were to multiply like the first fraction on top and bottom by the square root of 5 minus x squared, I'm gonna get like negative and then 5 minus x squared in here for the first fraction. For the second fraction, I have x squared, and then as a common denominator, I have square root of 5 minus x squared. Okay, so now let me break out the parentheses in here. So the negative would be distributed on the inside, so the first one will become like a -5, and then the second term will become a positive x squared, right? So then I'm going to go ahead and combine the like terms in here. So then it becomes 2x squared minus 5 divided by square root of 5 minus x squared. Okay? And, okay, first of all, before I move on, let me put back the answer in here. So the top part in here is 2x squared minus 5, and the bottom in here is the square root of 5 minus x squared. And make sure you don't forget this bottom, okay? So, like, from previous, like, bottom, we're going to get 5 minus x squared from the chi square part of the quotient rule, okay? Let me get rid of the sidewalk in here. All right, so what do we do with it? Well, because we have like f double prime in here already, we're gonna go ahead and plug this value of x in here into this formula of f double prime. And let me put in another color, blue. Okay, so if you were to plug that in, you're gonna get something like f double prime of 0, because we're talking about like this value of 0 in here, where you're gonna get 2 and then times 0 squared minus 5, and on the bottom we should get 5 minus 0 squared, and then square root of 5 minus 0 squared. And if you put all that into the calculator, what do you get? You're gonna get like a -1, or sometimes you're gonna get like a decimal number, and then that's fine, because we don't really care about like the value of it. We care about the sign of it, right? So in here, in this case, we have a negative number. Okay, so let me put it in another color in here to point out the importance of the sign here of f double prime of the number. And because it's less than 0, we talk about the second bullet point here where we have a maximum, okay? So now, well, I told you guys whenever we have like an x value, we always have to like plug it back into the original function to get the y value, right? And if you do that, in this case, you're going to get the y value, or f of 0. It doesn't matter like what notation you want to write down. It equals to square root of 5. Okay, so together, the maximum in this case, it is, okay, let me just put max. It is 0 comma square root of 5. Okay, and in fact, this one is a relative maximum. It's not like a absolute maximum. Okay. And if you ask me like, well, how do I know if that's like all the relative extrema in here? Because the question is asking me to find all of them, right? Well, you only have like one x value, right? So that means that you only have one extrema. So no, one maximum or one minimum. And in this case, it's a max, right? So it tells you that this is the only maximum, or this is the only relative maximum that you have in here. That means that your relative minimum is none. Or if you want, so just put like none, or just no relative minimum, okay, in English. But technically, like, all I care about is just this one, and as long as you write out this is the relative maximum, like, those are the final answers to me, okay? And if you want to double check your answer with the graph in here, like this graph in here is a half of a circle, it's the top semicircle in here, and as you can see, the highest point here is 0 and then square root of 5, or 2.24 in decimal version, okay? And before I move on, let me put a star in here. And just really quick, let me go back in number 1, because I just figured out, or I just remember that we didn't even compare our work with the graph, right? And I put it there for a reason. So let me take out some of the work in here. Okay, that's better. All right. So for the last example, I told you guys that we're gonna have an inflection point at 0, 0, right? So let's check whether that's true or wrong, right? So we're gonna always go from left to right, right? So we have like 3 or 4 branches in here. This branch in here look to me like a downward U, and this to me is like an upward U, and this to me it is, what is it? If you were to extend it, it's gonna look like upper U, and this to me is a downward U, right? So okay, so this is like, so from here to here, it changes the shape, right? And from here to here, it also changes the shape. And from here to here, it also changes the shape. So we should have 3 inflection point, right? But unfortunately, we're gonna cross this value out because it's not like defined for the original function. It's not a part of the domain. So that narrows out like one of the inflection point. We're gonna do the same thing with this one because x equal to 1 is not a part of our domain. So 3 minus 2, we only left with one inflection point, and it's right here where it equal to 0, 0. Okay, so then just to confirm with the graph in here, we're supposed to get 3 inflection points, but due to the restriction of the domain of the problem, we only end up having 1 inflection point. Okay, and the answer in here is 0, 0. Okay, so again, I'm not gonna ask you guys to like graph it, but as you can see in your like problem, if you were to do it correctly, this one is like upside down U, and this one is like a U shape in here. So as you can see from here to here, it changes. But this value of x equal to 0 in here is not the inflection point at all, right? Because, well, you don't have any point here, right? Just like the dash point here is supposed to be like a dash point in between. If you were to have an inflection point, then the graph, it will show a point. If it doesn't show a point, it means that it's like invalid at that point. It means that at that value, the function doesn't define, okay? And for your second example in here, if you do the correct thing in here, so if you notice, this one in here is a U shape, and then this one in here, upside down U. Okay, it has like two parts in here. So let me break that out a little bit. So this one is a U shape, and then from here to here, like somewhere in the middle, is this shape, right? And then from here all the way to here is this shape, okay? So we're gonna have like 1 inflection point in here and probably like 1 more in here. Okay, so you should have 2 inflection point, or like 2 extrema in here. And if I'm not wrong, where is it? Oh wait, this question doesn't even ask for inflection point. Okay, but just really quick, for this question, you should get like 2 inflection point. And as you can see in the picture, there's only like 1 loop. It means that you're gonna have like 1 relative minimum. Okay, and just for like the instruction of the problem, this one is your answer, and of course you have to find a value of x and y of that relative minimum. Okay, and this one is just like extra information in here, just so you know. There are like 2 inflection points, but it's not a part of the question. Okay, and now let's move on to number 3 in here, the last objective. So this one, it should be on your exam too, so make sure you pay like close attention to this one. Okay, so what does it mean by this diminishing like returns, right? It's the same thing as inflection point, okay? And what does it mean for inflection point? It means that the second derivative of it has to be set equal to 0, and after that we have to find x. And when we find x, we're gonna get the y value, and together this is the inflection point, okay? So in economics, the notion of concavity is related to the concept of the diminishing returns. Consider a function y equals to f of x, where x measures input in dollars and y measures output also in dollars, because we're talking about like business, right? Like economics. In the diagram in here, notice that the graph of this function is concaving upward on AC. AC, where's AC? AC is like this interval from here to here, right? So if you like piece them together and then extend it, if you like want to, it looks like an up, like a U shape, right? Like a regular U shape where it concaves upward, okay? And then it concaves downward on C to B, meaning from here to here. So if you were to extend this one like this, you will see that this one is like concave downward, or being like an upside down U, okay? So then the points in between where the changes happen in here, we call it the inflection point in math terms, or we call it the point of the diminishing returns in economics, okay? So on the interval A to C, each additional dollar of input returns more than the previous input dollar. And why is it more? Because we're talking about upward case, right? While by contrast, for the other interval from C to B, each additional dollar for the input returns less than the previous input dollar. Why? Because we're talking about concaving downward, okay? So this one we have like a more, and this one we have like a less in return. So the point, this point here, is called the point of diminishing returns, okay? An increasing investment beyond this point is usually considered a poor use of capital, okay? So what does that mean? If you invest like too much into a into like your business, and then your business is kept like going down. So say, okay, let me put it in pink. Like this is the input, right? So if you invest like more and more and more money in here, and as you can see, it's going down, right? it's not a good investment. That's why it's a poor use of capital. Okay, it means that, well, your money is not like wisely used. Okay, so if I were you, I'm gonna go like underneath of the inflection point. I'm not gonna try to like go over an inflection point so that I can earn more value. Okay. All right, so let's apply that into the application problem that we have in here. So the revenue R and the amount spent on advertising X is R, that function, where X is in between 0 and 400. Identify the point of diminishing returns. Okay, so what does it mean? We have to find the second derivative, set it equal to 0, solve for X, solve for Y, right? That's the whole thing we have to do. So let's get it done. First derivative, R prime, it equals to what? It equals to... Okay, first of all, let me break this down to like two pieces so then it's easier for us to do, right? So it's going to be like 600 x squared divided by 50,000, and then minus x cubed, and then 50,000. Okay, for the first function, notice that I can cancel like, I can divide both top and bottom by like 100 in here. So in short, that will give me a 6 on the top, and that will give me a 500 on the bottom. Okay, after I simplify it, right? Okay, so set aside that. The derivative of this is what? Well, it's gonna be 1200 over 5. Okay, you know what? Here, let me just take it slow, right? So this is like 12x divided by 500, and this is 3x squared divided by 50,000, right? And if you want to get the common denominator, well, you can multiply the top and bottom of the first fraction by 100. So it's gonna be like that, and then for the top part, you're gonna get like 1200, right? So putting that together, we're gonna get 1200 x minus 3x squared divided by 50,000. Okay, and then what do we do next? Well, we have to find the second derivative of that, right? So we're gonna do the same thing. We're gonna split them into the first fraction like this, and then also the second fraction like this. Okay, so in short, if you do it correctly, you're gonna get 1200 minus 6x divided by 50,000 in here. And next step in here, what do? We're gonna have to set it equal to 0. So let me get rid of some of the work in here really quick. Okay, and what happened if we set it equal to 0? Well, the top part ended up being 0. That means that 1200 minus 6x equal to 0. And if you do the correct algebra for this one, you get x equals to 200. And now that we have x, we're going to plug it back into the original function to get y. And this one is just like calculator use. If you put it like correctly into the calculator, you're going to get 320, okay? So to figure out whether this point here is indeed a point of diminishing return or not, well, okay, a lot of people make like a common mistake for this one, okay? Like, this is not the final answer. No, okay? This is not the final answer. You have to check it. How do we check it? Well, we have to set up a table of sign like before. So we're going to have the x value in here, and we're also going to have like the second derivative in here. X, it goes from negative infinity all the way to positive infinity, and then we have like 1 point in here, that is 200. So for x equal to 200, we know that the second derivative equal to 0, and now we have to do the table of size for it. So say in between like the first interval, I'm going to do like 100, and then for the second part, I'm going to do 200, and if you put it correctly into the calculator, you're going to get a plus sign here and then a minus sign here, okay? So in here, in this case, our double prime, it indeed changes from positive to negative, right? So there's a change in sign here. So that means that this point here is indeed the point of diminishing return, okay? But for like sometimes, like I'm gonna say like in the test or something, when you get like an answer, when you get the point here, and then if you don't plug that in this table of sign here, sometimes it doesn't give you any change at all. What do I mean by that? It means that it could be like plus to plus, right? Or like minus to minus. And that doesn't do anything because it doesn't change anything at all. So even though you get like a point, a solid point of x and y here, it's not the inflection point, and it's not the point of diminishing return because there's no change in the size of double prime. Okay? So the conclusion in here, it is the point of diminishing return. So let me put it like point diminishing return, PDR. It equals to what is it, 200 for the x, and then 320 for the y. And this is my answer. Okay, for your part, you have to do this problem. Okay, and again, if you have any questions or anything, let me know. Okay, thank you for your listening. Take care and have a great day. Bye bye.